Hello, everybody, and welcome to the Law Physics webinar cycle. I am the host. Physics webinar cycle. Sorry, I am the Law Physics webinar cycle. Okay, so I have the feedback from the YouTube streaming. So, okay, welcome to the Law Physics. I am Roberto Lineros from Universidad Católica del Norte in Chile. I'm going to be the host today. And today we have a very special guest. He's Andre Frankenthal. He obtained his PhD from Cornell University and also the master's degrees, and the bachelor he did it in the Reed College. Now he's a postdoc fellow with the Dickey Fellow at Princeton University, and he wanna talk about the squeezing the proverbial lemon, how to prove new physics with all particle accelerator. Welcome, Andre, and the stage is yours for your webinar.
Thank you very much. Thank you very much, Roberto, and thank you all for inviting me. It's really great to be here. So let me just share my screen, and then we can get started. I'm gonna move my and can you all see?
Perfect.
Perfect.
Yes.
All right. Okay. Yeah. So yeah, thanks again. And my title is How to Probe New Physics with Old Particle Accelerators, all those, new and old in quotes. And of course, because new and old are very relative concepts, my new physics can be your old physics and vice versa. But I will try to make this more concrete throughout the talk. And my goal for today is to sort of show you many different ways that we can use existing accelerators to squeeze more like interesting physics out of those existing facilities that were built sometimes even a long time ago. But I want to start by just briefly recapping the evolution of particle accelerators, because I personally think it's quite fascinating how far we've come. So starting with the very first accelerator, which was the cyclotron built by Ernst Lawrence at Berkeley in 1929, which accelerated protons to an energy of 100 keV. And for reference, of course, the mass of the proton is 1 GeV. So that was the very first accelerator. It fit in your hand, as you can see in this photo. Quite cool. But then already in 1953, we have the first synchrotron accelerator, the Cosmotron at Brookhaven National Lab. And this already accelerated protons to an energy of 3.3 GeV now, right? And this is in like 20 years or so. Followed by that, we have the SLAC, the Stanford Linear Accelerator in 1966, which accelerate electrons and positrons to an energy of 50 GeV. And I should say this is just a subset of all the existing accelerators, but it sort of showcases the evolution that we've had, right? So after SLAC, we had, for example, Tevatron, which was first started at 1983 at Fermilab. And that was the first time we were able to break the 1 TeV barrier, so accelerating protons and antiprotons to an energy of 1 TeV now. And then finally, we have the Large Hadron Collider at CERN in 2010. It started operations, and this accelerates protons to an energy of 7 TeV, right? So you can see that in less than 100 years, we went from 100 keV to 7 TeV. So many orders of magnitude improvement in energy reach. And this is, I think, quite impressive. I mean, it is very impressive. But there is another metric in which we advance quite a lot, and this is less noticed generally by people, but that's the sort of the luminosity, the beam intensity. So just to give you a sense of the beam intensity at SLAC, this was about 10 to the 29 inverse centimeters squared per second. So this is sort of a measure of how much of the beam intensity that you're able to use in your collisions, right? It's not a perfect metric, but I think it shows also the progression, because if you look at the Tevatron now, in 1983, we went from 10 to the 29 to 10 to the 32, right? So that's already 3 orders of magnitude improvement in this beam intensity, in the luminosity. And then at the LHC, this went even further to 2 orders of magnitude to 10 to the 34. So, in like this 50 years, we also like increased our intensity by 5 orders of magnitude. And this is really cool. And it sort of will be important for what I talk about in the rest of the talk, is just how much beam intensity we have available. So with all of this, many experimental accelerators and experimental, collider experimental programs, we're able to really complete the standard model of particle physics, which you can see here, a sketch of all of the different particles. I'm sure a lot of people have seen this sketch before, but so we have since 2012, we also completed that with the discovery of the Higgs boson. at the LHC, right? So this is really it was a very laborious effort to complete this picture of what the standard model looks like. But we also know by now that the standard model is not the full it doesn't describe nature to its full, it's still missing some pieces. So nature is not totally explained by the standard model. And I'm just putting here some arbitrary choices of like things that we don't yet, that standard model cannot explain, that we know about. So the fact that neutrinos have masses, we know that this is true experimentally, but it's not included in the standard model. The fact that the Higgs boson is so light, this is actually, some people, say that that's not a problem. Some people do, but, it's something that we don't fully understand yet. The fact that we have so much more baryonic matter than anti-baryonic matter in the universe. This is baryogenesis. And then my personal favor is the existence of dark matter, which currently is not predicted at all by the standard model, right? So that's what I'm going to focus on sort of dark matter and how we can sort of, experimentally probe that from an accelerator perspective. And just to sort of, highlight that we do know a lot about dark matter. We just don't know exactly what it is, in terms of particle physics, but we have lots of evidence for it from, astronomy, astrophysics and cosmological point of view. So here's some of these pieces of evidence going from like smaller to larger scale, right? So in the intergalactic scale, we know, for example, from galaxy rotation curves that they're not. So if you plot the velocity of sort of the luminous matter, the rotational velocity as a function, of the distance from the center of a galaxy, you measure that. This is the data here in yellow and blue, and then you compare with what you expect from just that luminous matter that you observe. It's very, very different, right? So this would be explained by the existence of some dark matter that's not visible to the naked eye. That's one famous piece of evidence for dark matter. Going a little bit further in scale, extragalactic, we have the Bullet cluster, for example. This is two galaxies that sort of collided, that went through each other, and in this process, the gas from the two galaxies sort of separated from their dark matter distribution because the gas is more frictional than the dark matter, and so you can see the colorful gas and the dark matter distribution that was reconstructed from gravitational lensing, and you can see that they're very different. And this is like a very lucky thing that we are able to observe in the sky, and that shows really that these things are two different things, like the gas, the hot gas in the galaxy, and the dark matter. And then finally, going even further, even larger in scale, we have the cosmic microwave background, where it really gives us a very neat evidence for the existence of dark matter and also dark energy. We can even estimate roughly how much of each in the universe we should have just from the CMB, the cosmic microwave background spectrum. So we do have a lot of evidence for dark matter, but we don't really know from a particle physics point of view what it is. And that's kind of one of the sort of open problems in particle physics and particle astrophysics, right? And so the way we think about dark matter in a particle physics setting tends to be in terms of like a dark matter particle, right? And so here's a sketch showing in the, I think you can see my cursor, yeah. So in the x-axis you have the mass, and in the y-axis you have the interaction strength between the dark matter and standard model particles, right? So this is just a sketch, but the idea here is that if the dark matter is too heavy and too faintly interacting with the standard model particles, then it can be very hard to discover. That's the purple region here. And on the other corner, if the dark matter is too light and too heavily interacting, we probably would have already have seen it, right? So the dark matter, there are some limits in where the particle dark matter could be, which is this white region here. And in this left lower left corner, it will be like a weakly interacting light dark matter, and on the other corner will be a sort of strongly but heavy interacting dark matter. So that's kind of the where we look for dark matter, but there is another narrow band inside this white region, which is this is the idea of a thermal dark matter, right? So this is the dark matter. So if your dark matter mass and coupling interaction strength happens to be inside this narrow red ribbon, then you have this very interesting connection to cosmology, because now your dark matter has just the right parameters to be the dark matter that we observe in the universe from all these astrophysical observations, right? So within this region, this narrow band would explain the so-called dark matter relic abundance. So any dark matter models that predict dark matter that fits here inside this red band is a thermal dark matter model. And that's a very interesting target to look for dark matter in generally. And then furthermore, if you look inside this red band and then you look at the 100 GeV mass, that happens to be the scale of the weak force, the weak interaction, 100 GeV or so. So there's this idea that if the dark matter particle sits around 100 GeV of mass, it could have an interaction with it could like also be weakly interacting in the sense of the weak interaction, right? And this is the idea of the WIMP, the weakly interacting massive particle, for a dark matter particle that would also interact weakly in addition to gravitationally. That's the so-called WIMP miracle. Is that the fact that this red ribbon actually is compatible with a weak scale dark matter mass. So in particle physics, this has been sort of the canonical view of dark matter that has guided a lot of the experimental efforts for the past 40, 50 years even. Like, it's the idea of that a single dark matter particle, a WIMP, that exists in addition to this very complex standard model of elementary particles that has quarks, leptons, gauge bosons, and so on. But and so looking on this model of a single dark matter particle, the way we look for those in particle physics, there's sort of three main ways, and that's kind of the experimental strategies that we use. So this is also another famous sketch of how we look for dark matter in particle physics. But if you imagine two particles interacting, two interactions, so you can read this sketch in many different directions, top to bottom, left to right, right to left. It has two standard model particles, two dark matter particles. If you start, let's say, from the bottom, so you start with two dark matter particles, they interact somehow, they annihilate, they produce some standard model particles like photons, neutrinos, or electrons. You can look for this annihilation of dark matter, the signal of dark matter annihilation in space, because that's what dark matter is for the most part. So we have lots of experiments looking for dark matter in space. This is called indirect detection, because you're not detecting the dark matter, you're detecting the products of its self-interactions. So just two examples of that is the Fermi-Lab telescope and the AMS-02 experiment. They're looking for signs of dark matter annihilation with different final state products. That's a very important avenue. Sorry. We can switch that diagram around and now start with one standard model particle and one dark matter particle, and they interact elastically. They come out. And what you can do is you can have a big detector on the Earth, underground, and you just have this large detector, and you wait for dark matter particles to cross the Earth and interact with your detector. And then that would be a dark matter particle interacting with some standard model particle in your lattice, in your detector lattice. And this is called direct detection because you're really trying to detect the dark matter interaction here directly, right? So this is just one example. It's a dark side experiment. And the idea here is you have all this lattice of nuclei, and then the dark matter comes and interacts with your nucleus or with your electrons around the nucleus, and then you sense that somehow. And this has been a huge, a lot of, there's been a lot of effort in the past, like I said, 40 years looking for direct dark matter, direct detection dark matter. And you can see sort of a summary of these results here. So this is showing now, these are exclusion curves in the sense of the cross section. So the way to read these kinds of plots is on the x-axis, you also have the mass. In this case, it's a WIMP mass because this experiments are looking for WIMP dark matter. And then the y-axis, you have the cross section. So that's again, the interaction between dark matter and standard model particles. And all of these lines, they are defining excluded surfaces above. So all of this green color parameter space has been excluded already by experiment. And so, so you have heavier dark matter to the right, and then you have smaller dark matter as standard model interaction to the left. So there's been you see lots of curves here. There's a lot of stuff, a lot of experimental effort to that on that. But what you see too on this left region is that, so the so-called low mass region, that there is a lot more white space, right? So this is the low mass region is more difficult to probe. You can see how these experiments all sort of fall off, like the sensitivity. And this is true in general. It's more difficult to probe low mass dark matter, and that's why you have more white space here. And then this is where I want to target my talk in the space of low mass dark matter. But I want to explain the last sort of method that we have. If we flip the diagram one more time, now we start with 2 centimodal particles, and we're trying to produce the dark matter in the laboratory. So we have a centimodal beam. So there's actually 2 ways you can do that. On top of here, you have fixed target experiments, on the bottom collider experiments. So either you have 2 centimodal beams, like beam of particles, they collide, and then you put all your detectors around it, and then you hope to produce the dark matter and to detect that somehow. So that's kind of a collider experiment setup. And then with the fixed target experiment, you don't have 2 beams, you have only 1 beam, and then you have a fixed target, and then but it's the same idea. You're trying to detect the production of dark matter in your laboratory, and then you put just detectors all around it. So that's kind of the idea for collider. Now you're trying to produce the dark matter. And I'll show you today 2 examples that I'm a collaborator with. One is a PADME experiment, and the other is the CMS experiment, one of each, right? And but I want to come back to that idea of a single dark matter particle, because, like I said, that's been a very canonical view of dark matter in particle physics. But the truth is that we don't really know what dark matter is, right? We really don't know, and there is no, there's no technical possibility to think about a more complex version of dark matter, right? So why does dark matter has to be a single WIMP particle when the center model is so rich and complex? So if you allow yourself to think of a complex dark sector, not just a single dark matter particle, then you can think of, there's a lot of things you can think of. This is just one example. We can have, for example, a stable dark matter and an excited dark matter state. You can have additional gauge bosons like a dark photon. You can have additional Higgs bosons even. So, the list, there's, it's infinite. You can think of many different kinds of complex dark sectors. And the nice thing about thinking of a complex dark sector instead of a single dark matter particle is that, well, the first advantage of that is that you are able to evade a lot of this very stringent dark matter dark detection constraints that I just showed you a few slides ago, and I'll show you that. And furthermore, you're also this also offers a lot of additional avenues that we can probe dark matter if we're thinking about a complex dark sector. So there's a lot of interest in I would say in the past 10 years or so to investigate additional complexity in the dark sector. And so the dark photon is actually one of those ideas, right? So the dark photon. So if you try to extend the dark sector from a single dark matter particle, one of the simplest things you can do is think of a new gauge boson, a dark photon. And this dark photon is essentially a cousin of the photon in the standard model. So it's the carrier of a dark electromagnetism. This will be like a 5th additional force. You may also have heard of that, this term 5th force. But a dark photon would be similar to electromagnetism, but operating only in the dark sector, except that if you assume the existence of a dark photon, then you automatically can get a portal between the center model and the dark sector via this special coupling called the kinetic mixing, right? So the dark photon kinetically mixes with the photon in the center model. This mixing is typically parameterized by this epsilon, the kinetic mixing coefficient. And this coefficient, so it's basically parameterizes the strength of this coupling between the photon and the dark photon. And this idea is very powerful because it allows you to look for a complex dark sector by looking for this dark photon being produced in our accelerators instead of the dark matter. And this is in the standard model, the photon is a very simple simple force, is a U1 symmetry, and so this is why it makes sense to think of a dark photon in the dark sector as like an additional U1 symmetry. So to sort of summarize what is the current dark matter model landscape, this is a sketch from the latest mass exercise here in the US, and it shows again in the x-axis is the mass of the dark matter and the y-axis is the interaction strength, and you can see, of course, the parameter space is very, very large in terms of dark matter mass, interaction strength. But I want to focus your attention to this area here, where you see, first of all, the classic WIMP that I just described at the 100 GeV mass or so. And that is sort of a subset of all thermal dark matter models. So dark matter models that are compatible with the relic abundance that we observe in the universe. And then the thermal dark matter model itself is sort of embedded into this idea of a complex dark sector. And this is how we sort of are typically see our search for dark matter in the sense that we can look for classic WIMPs, but we can also look for thermal dark matter models, and we can look for complex dark sectors and so on. And so what I want to focus on is on this question of can we search for dark matter production in the laboratory, and particularly at this low masses? This is the shaded region. So this low mass where the direct detection methods struggle. So I show you before, like in the left plot of the dark matter of the direct detection plots. Because if we can do this here, if we can look for low mass, like in the MeV to GeV range for dark matter, that's a very compelling space to look for, and where the direct detections struggle. So this is the goal. And so to do that, I'll show you two efforts in that direction. So first, I'll talk about the LHC and the CMS. They're sort of how we can exploit their capabilities to the fullest to sort of probe exactly this kinds of rare and low mass phenomena. And then later, I'll talk about using a different setup to look for dark photons specifically with PADME and DAFNE. So I don't think the Large Hadron Collider needs a lot of introduction, but here's like the mandatory slide on the Large Hadron Collider. It is the biggest machine ever built by humans. It's a 27-kilometer ring in Geneva, Switzerland, and also France. And it accelerates protons, accelerates and collides protons to, with a center mass energy of 14 TeV. So it's really, really energetic. And it's a really huge machine. And it has 4 main experiments around this ring: the CMS, LIS, Atlas, and LHCb. And you can see some photos here of the machine. And inside the machine, I'm a part of the CMS collaboration, the compact muon solenoid experiment. And CMS, the main point of CMS is that we are general purpose detectors. So we collide the protons and we try to instrument every corner of the detector as much as possible around the collision point. And we try to just reconstruct every single particle that's produced when protons collide. So that's the idea. And our detector operates in these layers, and onion layers. Each layer is a different sub-detector. So we have trackers, we have calorimeters, we have muon detectors, and so on. So CMS is a general purpose detector that tries to be agnostic about the particular kinds of physics that you want to investigate inside the LHC. So because of that, because of the energy and the intensity of the LHC, it really allows us to access a vast range of mass scales. So this is another sketch showing sort of as a function of mass, the different kinds of physics that we can explore with the LHC. And you can see it goes from several GeV to a few TeV in mass. And then on the top here are standard model physics, such as Higgs boson physics and top quark physics. And then the bottom is so-called BSM, beyond center model. So where we're searching for new models that go beyond the center model, and in particular dark matter, supersymmetry, extra dimensions, and so on. So there's a lot we can do. And this is why it's good to have a general purpose detector, because we can pick the kinds of physics we want to do, and we can do a lot of it. But again, you see also on this left corner, it's also sparsely populated. So this is, again, that low mass region that I defined earlier. So there's plenty of room in the bottom, at the bottom here too, to explore low mass physics. And so in the next, I'll describe why probing low mass region is so difficult and what we can try to do to mitigate that. And so yes, why is probing low mass signals so hard? Here's just a random example of a proton collision that we see in CMS. So the protons are coming from these arrows here that I showed. They collide. They produce hundreds of tracks, low momentum tracks and calorimeter energy deposits. So the point is that there's a lot of information that gets created when the protons collide, and that we need to absorb and process to really tell what's going on, right? And so just as an exercise, all of this information that I'm showing here, it's about 1 megabyte per collision event. Now the LHC operates at about 40 megahertz. So at 40 megahertz, so it collides proton bunches once every 25 nanoseconds, which is a really huge rate. So if you multiply this together, this would imply a data bandwidth of 40 terabytes per second, which is, of course, impossible. Like, we can't handle this much data, unfortunately, right? And so the idea of this is that this means that we have the unfortunate needs for triggers. Triggers are sort of a very important concept in collider physics, because we cannot save all the information that we create, that we produce. And so the idea of the trigger systems is that we'll try to we'll be smart about which what set of information we store, and in particular, which proton collision event we want to save to storage. So really the limitation roughly is that we have at the end of the day, we have to have a data bandwidth of 1 gigabyte per second, not 40 terabytes per second, unfortunately. That's what we can afford. So to get to that, we start out with our proton collisions at 40 megahertz, so once every 25 nanoseconds. We have a first layer of the trigger called the hardware trigger. This is a very fast, like FPGA, ASIC-based, sort of electronic-based trigger system that selects events with coarse information, with coarse detector information. And it manages to reduce our trigger rate, our event rate from 40 megahertz to 100 kilohertz. So this reduces the amount of events we have to deal with. That's not enough though, so we need an extra layer. This is called a software trigger layer. This one runs on actual CPUs, like processors. It's slower, but that's okay because we have only 100 kilohertz of events to deal with. But it can use a lot more information from the detector, right? And so it's okay. And at the end of the day, we reduce that 100 kilohertz further down to 1 kilohertz. And for a 1 megabyte per event, that gives you exactly the 1 gigabyte per second bandwidth that we can afford. So this is what the trigger system does essentially in TMS and Atlas, is to select interesting events to keep. And just to give you a sort of a feel for it, like one typical trigger would be, let's say, for this we'll save for this trigger path, we'll save only events containing at least 2 muons that were produced with some momentum greater than 20 GeV. So that's kind of how we implement the triggers. We have a lot of those paths, and that constitutes a path trigger menu. And then if any event satisfies one of those paths, it gets stored. And so coming back to this picture of the same collision that I showed you before, here we have the protons colliding. The direction of the collision is called the longitudinal direction. And then the plane that's transverse to that collision direction is called the transverse plane, the transverse direction. And so we divide our objects, our reconstructed physics objects, into a high PT. These are objects that are produced perpendicular to the beam direction. So they have lots of transverse momentum. This is what the high PT means. But then we also have all of these other objects that are this low PT tracks in red. So we produce a lot of low PT stuff. So these are particles that they are produced very, very boosted. So they are produced very collinearly with the beam direction. So they have very little momentum in the transverse directions. They're called low PT objects. And the problem, really, why probing low mass signals is so hard is that light particles, low mass particles, they're very low PT objects, right? So just to give you an example, here's a sketch. There's this particle called the eta meson that has a mass of only 0.55 GeV. So it's a very light, low mass particle. It gets produced copiously when protons collide because of QCD, but it tends to be produced very forward, very collinear with the beam direction. So in the transverse direction, it doesn't have a lot of momentum. And you can see that here from a simulation. This shows the distribution. I just simulated the energy of eta mesons that are produced in the LHC. You can see it goes to thousands and thousands of GeV. So this particle is extremely energetic. But if you look at the transverse momentum, the eta meson PT on the right, you see it's just a few GeV, right? So there's this huge difference between the energy and the PT. So that's one part of the problem. The second part is that the trigger must focus generally on high PT objects. If we were to say we cannot afford to save all the low PT objects, so we typically focus on the high PT objects. And so for this particular plot on the right, typically what a trigger threshold will be is this black dashed line here. So even though we produce so many eta mesons, we only store a tiny fraction of them, because they don't have enough PT to pass the trigger thresholds. That's the problem of probing low mass signals and colliders. To sort of overcome this challenge, we've created a few different systems, I guess, systems and techniques. And one of the more popular ones these days has been the idea of the data scouting, right? And the data scouting here is actually a very simple idea. So what if instead of trying to limit the number of events that we store because of our data bandwidth limitation, what if we just decided to throw away some of the data in each event that we don't particularly care about for our goals? So the idea is that instead of saving each event completely, we just save a part of an event. And for the same bandwidth, we are able to store many, many more events. So this is data. This is called data scouting. And so you can see like a sketch here. So at the software trigger level, instead of saving the full event, we just say, let's just save a little part of an event. And this we can have a much higher rate than 1 kilohertz with a fraction of the data bandwidth. So this is a very high level introduction to data scouting. There is a review paper that we just submitted to Physics Reports. It's also on arXiv if you're interested about the more technical details of the data scouting, and also data parking, which is a related technique. But just to give you an example of what scouting does, right? So here's one example that's called muon data scouting. And in muon data scouting, the idea is that we are only going to save the muons that are produced in each proton collision instead of all the different tracks, the hundreds of tracks and calorimeter energy deposits. Let's say that we just save the muons. Then it's only a little bit of information, and effectively what that does is that allows us to shift our trigger threshold much, much lower. So instead of the black curve that we can only save a few eta mesons, now suddenly we can shift that to the left and save many, many more events that contain eta mesons, because we are exchanging event information for a number of events. So this allows us effectively to have a trigger rate much, much higher. And you can see the result on the right here. So this is a plot from this paper showing the dimuon invariant mass distribution that was collected with the standard triggers and with this technique scouting in green, right? So you can see, in particular at the low masses, so at the low dimuon invariant masses below 40 GeV, just how many more events we're able to store with the scouting technique. It's really, really a really big difference. So, and for those who don't know the dimuon invariant mass, when I'm talking about dimuon invariant mass, all I mean is if you take two muons here and you sum their forward momentum, that equals to if an X particle decays to two muons, then the sum of the forward momentum is going to equal the mass of the particle X that decayed to these two muons, and for that we call the dimuon invariant mass. So this is what we're plotting here is dimuon invariant mass, and you can see here for the Z boson, which has a mass of 90 GeV, that Z boson is decaying to 2 muons, so we can see a peak at that value of the mass. So this is what the dimuon invariant mass is. Okay, so now here is a more complete plot showing the dimuon invariant mass collected with the scouting triggers, right? So again, on the right here, you see the same Z boson as before. I think I lost my cursor. Here it is. So here's the Z boson, but now this is in the log scale in the x-axis, so you can see all these other resonances at low masses too, so below 10 GeV or so. And you can see that this is a very cool thing because the scouting allows us to really probe this very low mass particles that are decaying to dimuons too that we couldn't do with the standard technique. So we have all these peaks, and the question is, can we use this neat spectrum to search for new physics in these low masses? And so I'm going to focus on this very, very tiny peak here, which is the peak of the eta meson. I actually already mentioned the eta meson to you, but just for a formal introduction, the eta meson is a neutral pseudoscalar, so it has spin 0, and it's a mixing of all the light quark states, so up, down, and strange. And like I said before, it has a mass of only 0.55 GeV, so it's a really, really light particle. And for the technical audience here, it also has a very tiny decay width of only 1 keV. So I'll show you why this is interesting, and it's funny because this peak here of the eta meson looks so tiny, but this is very deceiving because the eta meson is copiously produced in the PP collisions at the LHC, but like I said before, at forward angles, so very low PT. But it's still visible in the scouting spectrum that we collected with this scouting technique, and if you zoom in on this spectrum, right? So now instead of the whole spectrum, I'm just showing between 0.52 and 0.57. So you can see we can fit this and we get about 5 million eta to 2 muon decays from this scouting data set. Now 5 million is a really huge number, but the thing is the probability of the eta meson decaying to 2 muons is only 10⁻⁶. So what this means, if you work backwards, is that we have access to about 10 to the 13 eta mesons, and this is a really huge data set, right? So this tiny little peak is deceiving because just the fact that we have access to 5 million of those events is really huge. To put this into context, right, this makes CMS competitive with a lot of experiments in the past and in the future that are dedicated to light meson physics, such as the eta meson. So, for example, the first observation of the eta to 4 electron decay done with the Chloe experiment used only 10 to the 7 eta mesons. You can see here, this was in 2011. Similar for the eta to 2 muon observation, that this first decay in 1980 was 10 to the 7, used 10 to the 7 etas to produce. And then we have this dedicated experiment for eta mesons that's been proposed at Fermilab. It's called RadTop. It's an experiment that was proposed to study etas and the cousin eta prime mesons. And they are proposing to produce 10 to the 13 etas also per year, right? So this means that we're really up there with these kinds of experiments that are dedicated to light meson physics. So once we realize that we have this huge sample of eta mesons, the first thing that we do it's to contemplate the study of this rare decays of the eta meson. So here's a sort of a table. This is from the particle data group showing some of the decay channels of the eta meson, and on the left, and then on the right, this is the branching fraction, the probability of decay of the eta meson to that channel. And just to highlight some that have actually never been observed before. So the eta to 2 electrons has never been observed. Similarly, the eta decaying to 2 electrons and 2 muons and to 4 muons has never been observed. You only have upper limits on those decay channels. Here's the Feynman diagram showing what it would look like for an eta meson to decay to 4 leptons. So first it decays to 2 photons. Internally, these 2 photons convert to each to a pair of leptons. So you get 4 leptons in the final state. All right. These has never been observed before because they're very rare. However, we have a huge sample of eta mesons now access to, and with the scouting technique. So the idea is, can we actually look for such rare events, processes? And I should mention that there's actually a lot of motivation, phenomenological motivation in the literature for doing these kinds of rare eta decays. So for example, I won't go into detail, but you can use them to measure the transition factors to better study QCD. You can also improve the precision in the theoretical prediction of the muon G-2 anomaly. This is the light mesons also enter here. And then finally, you can search for new states, standard model and beyond standard model states, such as true muonium and dark photons. And I'll talk about that more later about this particular application of this. But there's lots of things you could do with eta mesons. And so first, I wanted to show you what a candidate eta to 4 muon decay looks like, right? So with the scouting data set, we're actually able to observe this very, very rare decay of the eta meson. And you can see what that looks like here. So this is another event visualization. So, and the sketch is that essentially we have this eta meson that it's not visible. It decays to 4 muons, and the muons is what you're observing here, detected by the muon detectors. These are the 4 red tracks, right? So if we collect enough events that look like this, right? So we collect enough of them, and then we compute the 4 muon invariant mass of all the 4 muons. So we're just summing the 4 momenta vectors of all 4 muons, and then we plot that histogram. We histogram that. Then you can very clearly see a huge peak around the eta meson mass, right? So this was published last year. We observed for the first time this decay of the eta meson to 4 muons with a huge statistical significance. You can see the size of the signal compared to the background is really striking, and we're only able to do this because we have the scouting technique. And we can go further. We can actually measure the decay probability, the branching fraction of this decay. So we did that by comparing that to a reference channel, which is eta to 2 muon decays. We found this number, this ratio is 0.9 plus minus 0.1 times 10 to the minus 3, which we can convert to an absolute decay probability. And that's, the branching fraction of this decay is eta to 4 muon decay is 5 plus minus 1.3 times 10 to the minus 9, which agrees with the standard model prediction. That's good. But the remarkable thing is that this constitutes an improvement of over 5 orders of magnitude compared to the previous measurement, which was only able to set upper limits of 10 to the minus 4, right? So we went from 10 to the minus 4 to 10 to the minus 9 now, and this is the kind of thing that scouting allows us to do now, exploring this very low mass phase space. And so, yeah, going back to the sketch of these kinds of things we can do, we just added, an extra point in this sub-GeV space that we can probe, and this is a new window for CMS to explore that was not available before. And so the question is, what else can we do with this? Can we go even lower in mass? Can we search for other things within this space? So for the next couple of minutes, I'll just sort of talk about ongoing projects and things that we're doing that are derived from this first measurement of the eta to 4 muon decay. And that, again, were also not possible really before. So the first thing is we can search for the related decay. Instead of doing eta to 4 muon, we can search for eta to 2 muons and 2 electrons reduction. So here we're just replacing 2 muons with 2 electrons. But the interesting thing about this is that if we can measure both of these decays with enough precision, then we can test for lepton flavor universality. So we can actually test that the coupling to electrons and to muons is the same as it should be as predicted by the standard model. So this is called lepton flavor universality. So we can do that with the eta meson at 0.55 GeV if we can measure this well. This is something that's ongoing work, and it actually was really not even possible before last year, or actually 2022 now. It was not possible before because we just didn't have the scouting setup adapted to study electrons as well. It was just muons. But now we can do that, and so we're doing that. This is something very interesting. We can also use the same sort of setup to look for dark photons now. So instead of looking for eta decaying to 2 photons and then each photon decaying to 2 leptons, now we're looking for eta decaying to photon and a dark photon, and then the dark photon decays to 2 leptons. So we can look for dark photon production in this way, coming from the eta meson decay. And remember, we have about 10 to the 13 eta mesons. So we're kind of like an eta meson factory in this way. And so this gives us the potential to really surpass, to at least match, but possibly even surpass the world leading sensitivity in the sub-GeV mass range for dark photon searches. So here you see this plot is a summary from this review paper showing all the different dark photon search experiments. Here now, instead of WIMP mass on the x-axis, we have the dark photon mass on the x-axis. And on the y-axis, it's also an interaction strength, but it's the epsilon, which is the kinetic mixing coefficient that I introduced back in the slides, right? And we have lots of experimental efforts to that, but you can see here at the sub-GeV, it's dominated by the LHCb experiment. And what we're investigating is that we really, using this scouting technique, we can very seriously compete with the LHCb in this regime of trying to probe very low interacting dark photons. So that's something that's also exciting and ongoing. Finally, we can also look for true muonium, and true muonium is actually not a new, beyond standard model thing. It's actually predicted in the standard model, but true muonium is the idea of two, that you can have a bound state made of 2 muons. And that's similar to the muonium, which is a bound state made of electrons and muons, 1 electron and 1 muon, and the positronium, which is a bound state of 2 electron or 1 electron and a positron, or even atoms, which is a bound state of protons and electrons. So we can actually look for that. So the thing of the true muonium is that it's very light. It has a mass of 2 times the muon mass plus some binding interaction strength, interaction energy, sorry. But the true muonium decays to a pair of electrons or dissociates to a pair of muons if it interacts with matter. And the probability of the eta meson decaying to a true muonium instead of a dark photon is about 10 to the minus 10, which is really, really low. But remember, we have 10 to the 13 eta meson, so this is not actually impossible. It might actually be possible. So this is a unique opportunity that presented itself in CMS. It's something that we're investigating, whether we can actually, it's within the realm of possibility. Now we have to actually search and investigate and see if we can do this. But it's exciting that we can even think about these kinds of things. Okay, so I hope I convince you that CMS actually has a lot of new sensitivity to low mass physics. I show you one example with the eta meson, but we can look for dark photons in the sub-GeV range. We can do different kinds of, we can search for true muonium. We can do different kinds of things, and this is very exciting because because it's a very difficult phase space to probe. So it's something that we can actually explore now. And so with the last few minutes, and the other conclusion that I wanted to make is that this data scouting technique that I introduced is really essential to be able to search for this kinds of light dark matter like a dark photon in this MEV to GeV range. And I hope you're not hearing my Skype things, because are you? You are? Okay. Oh, I'm so sorry, because
But it's okay. Don't worry, Andre.
I'm just gonna quit. Yeah, because I did put do not disturb, but I guess Skype doesn't respect that for some reason. Anyway, okay, so so yeah, so that data scout is really key for searching for light dark matter in this shaded region, and that's something that we're pursuing now. But I want to spend the last few minutes talking about what can we do. Can we go even lower in mass? Can we go below 100 MeV, for example? This is actually something that's getting really difficult for a collider to do, but it's not something that it's impossible. We can actually do that using a whole different setup that I'll introduce now, and this is called the DAFNE and PADME experiment. So that's what I'll spend the last few minutes. The DAFNE complex is a accelerator called Double Annular Phi Factory for Nice Experiments. It's a very nice name, and it's located in Italy in the Laboratorio Nazionale di Frascati. It accelerates positrons and electrons, so not protons anymore, but positrons and electrons to energies of 500 MeV. And it was originally built to study phi mesons, which have a mass of 1 GeV. That's why it's called DAFNE. And this was built back in the 90s. It first started operating in 1997 for Chloe, for the experiment called Chloe. And you can see some pictures here. And what I want to talk about is this new experiment called PADME, which stands for Positron Annihilation into Dark Matter Experiment. This was also an acronym that was worked very hard, like and it has a Star Wars reference if you got it. But PADME is a particle physics experiment that has only about 30 people. And that's a very rare thing in particle physics these days. So it's kind of exciting that we can actually do interesting particle physics with not that many people. You can see a subset of the people, a photo of the subset of the people here. But PADME is a fixed target experiment. And the key thing is that it allows us to probe dark photon mass, dark photon in the mass ranges of 2 to 22 MeV. So it's very, very low, sub-GeV, sub-100 MeV dark photons. And I'll explain how it works. But in that way, it is very complementary to colliders, right? Because colliders it's really hard to go that low in mass sensitivity. So I already talked a little bit about how fixed target experiments work. But just to highlight, you have a fixed target here. You have a beam, in this case, a beam of positrons. They impinge on the target. This is an active target, and then you have these detectors all around the target. And what you're hoping to find here is you're trying to get the electron and the positron to annihilate. So a positron from the beam and an electron from the target, and they annihilate and they produce a photon and a dark photon. And in this case, the dark photon will just escape our detector. We're not going to see the dark photon at all, but we can measure the momentum of all the other particles in this system. So measure the momentum of the beam, you assume that the momentum of the target is, it's a fixed target, so it's not moving. And then you can measure the momentum of the photon, the outgoing photon. And if you do all of that, you can reconstruct the missing mass of the system, which is what corresponding to the mass of the dark photon that escaped. So this is called a missing mass technique in the fixed target experiment. And so the dark photon would appear as a bump in the missing mass spectrum. And here you see some simulations for different signal hypotheses, different dark photon masses, what it would look like. So we can look for that. Essentially, we're looking for a bump in the spectrum on top of any backgrounds. And so just is to show you what the actual setup looked like. Unfortunately, here I inverted the orientation. So now the beam is coming from the right. So you have the beam coming here from the right. You're hoping to, again, produce the dark photon and the photon in the target. Then we have a magnetic field. The magnetic field basically serves to deviate the non-interacting beam away from our calorimeters, right? So we have this magnetic field, and then we have a beam dump here for the non-interacting beam. And then the photon, we expect to hit our calorimeters here. I'll talk more about that. The dark photon, like I said, escapes our detector. And then we also have a veto here, which serves to reject some backgrounds. But this is essentially the setup. It's kind of, and this is like order of meter, scale. So it's not very big. So yeah, the calorimeters are sort of the main feature of the experiment. And so just to talk a little bit about them, so we have two of them. We have the main one, which is the electromagnetic calorimeter. It's 600 scintillating BGO crystals that we took with permission from the old L3 experiment at lab. And it's a very good calorimeter. It has a very good energy resolution, 2%, but it's not very fast. So the scintillation time of BGO is about 300 nanoseconds. And then we have this hole in the middle of the calorimeter, the square hole, where flush with the, downstream of that calorimeter, flush with it, we put the small angle calorimeter, which just fits it right. So it's a 25 Cherenkov, 25 crystal calorimeter, small angle calorimeter. It's a Cherenkov calorimeter, meaning that it's very, very fast, because lead flow right that time is only 3 nanoseconds. So it's like 2 orders of magnitude faster, and it has decent energy resolution. So I'll explain why we need both calorimeters. So this is the main physics backgrounds that we have to contend with. So as a reminder, the signal that we're looking for is 1 photon in our calorimeter. So the positron and the electron annihilate in the target, dark photon escapes, and the photon hits our calorimeter. So just a single photon. But Bremsstrahlung emission can also mimic this signature. So instead of the positron annihilating with the electron, when the positron goes to the target, it feels the magnetic field of the nucleus, and it emits a Bremsstrahlung photon. And that photon could then go and hit our calorimeter. Luckily for us, the calorimeter, the Bremsstrahlung angular emission is very sharply picked around the beam direction. So if we just have this hole in the middle of a calorimeter, that's enough to really reject most of the photons that are produced by Bremsstrahlung emission. So that's why we have the central hole in our calorimeter. We just literally let the photons go through our calorimeter and don't worry about them. Unfortunately, that creates another background, which is the 2-photon annihilation. So here, so the positron and the electron, they do annihilate, but instead of producing a photon and a dark photon, which is the signal we're looking for, they produce 2 photons. This would usually result in 2 photons in our calorimeter, so would not be a problem or a background. But because of the new hole that we have in the main calorimeter, one of the photons could actually go into the hole. And then now this would look like a signal, because we have one single photon in our main calorimeter. This is why we add the second calorimeter, so that we can actually reconstruct, we can sum we see that we have a photon in this other calorimeter, we sum its energy with the photon on the main calorimeter. We'll see this is actually a background event and not a dark photon signal event. So that's the setup. I want to talk about the very first result that we actually released last year. It's not a dark photon search, but it's the cross-section measurement. So now we turn this 2-photon background into a signal, and we measure the production cross-section of E plus, E minus to 2 photons at a very low square root of S, 21 MeV. So this is our very, very first result, physics result, which is very cool. It's in good agreement with the standard model prediction. So we measure that to be 1.98 millibarons, which is consistent with the prediction within uncertainties. And the nice thing is that this is actually the very first measurement at this low energies, like sub-GeV since the 1960s, which is kind of crazy. When we're looking at the literature, we're looking for the similar results, and they're all from the 50s or 60s, which is kind of cool. So we have one of the most precise measurements of this production cross-section now. And with the last 2 slides, I want to talk about one thing that we're currently we're currently pursuing. This is a very timely thing. This is called the beryllium. Well, there's different names for this, but it's called the beryllium anomaly or the helium anomaly, carbon anomaly, and so on. But this is the idea of this. There was this result in 2016, this PRL, where this group, this nuclear physics group, observed some excess. So basically what they do is they strike a beam of protons into a nucleus of lithium. This lithium nucleus absorbs the proton and becomes an excited state of beryllium. This excited state of beryllium decays back to its ground state of beryllium, and by producing a photon, which then decays to a pair of electrons and positrons. And the idea is, if you measure the angular separation of the electron positron from the de-excitation of the beryllium nucleus, and you measure that, and you just histogram that, you can see here, this is the theta, the angular separation of the two particles, the electron and the positron. And there's this huge excess over the predicted background, which you can see highlighted here. And the interesting thing is that they did this in 2016, and since then, they found the same thing in a different system altogether, the helium and hydrogen and tritium. They also see this excess over the expected background. This excess is on large separation angles. So at 100 and greater than 100 degrees, you get this large separation angle, excess on the separation angle. And then they did that again last year or 2 years ago with carbon. So it's very interesting that this excesses we don't really understand where they're coming from, but there's three main possibilities. The first one is that there's some systematic issue with the measurement, although the measurement is very well understood. But it is a possibility. Maybe not as likely. The second possibility is that this is some kind of nuclear physics effect. Nuclear physics experiments are really difficult. Nuclear physics is really difficult. And so it's possible that there's some nuclear physics effects that we're just not understanding. That's actually certainly a possibility. But the third, maybe more exciting possibility is that this is some kind of new boson that goes beyond the standard model called a protophobic boson with a very, very light mass of 17 MeV. And if this new boson is also being produced by the de-excitation of the beryllium, it will tend to produce larger separation angles on average than the photon. So this would nicely explain all three results in a sort of consistent explanation. And the nice thing about a new protophobic boson of mass 17 MeV is that it's exactly within the acceptance window of PADME, which is 2 to 22 MeV dark photons. So with only a few detector tweaks, we're able to actually confirm or reject this hypothesis of this X17 is the name, this theoretical name of this hypothetical particle. But we can actually look for X17 with PADME just by doing very few detector tweaks. I won't go into details on the tweaks. I'm happy to talk about, but this is something that it's ongoing, and we're planning to release this result very soon because it's a very timely. We can do that ahead of several other dedicated X17 searches that have been proposed or are being under construction. This shows the sensitivity that we expect from PADME, and we can really close this window for X17 if we do, after we analyze our data. So this is actually something very exciting that's ongoing. So to conclude, I hope I've convinced you there's lots of interesting physics at low masses, including complex dark sectors that could feature light particles hidden from view, like dark photons or X17. And that the fact that we have this high energy and really high intensity accelerators really allows us to probe this new promising physics scenarios at this low masses. So I show you the example of the data scouting technique in CMS and how they can be a useful tool in the search for new physics. And then at the same time, specialized small experiments in particle physics really serve a very nice complementary role in this kinds of searches for complex dark sectors, like I showed with PADME. So we're going to have lots of more results with scouting and with PADME soon. So stay tuned for more updates. And thank you. I'm happy to take any questions.
Thank you very much, Andre. It was a very, very interesting webinar. I mean, the topic is very exciting. So just want to remind the people that are following us in the YouTube transmission that you can write questions for Andre, and we're going to address this question to Andre as soon as they appear. So for the moment, we're going to start with the question from here for the people in the Zoom session. I don't know, Joel, Alejandro, or ask questions they want to ask to Andre. Joel has one. Oh, Andre, Walter. Okay.
Okay. So thank you for the webinar. It's been very, very interesting. I was wondering regarding the scouting. So you're taking only certain part of the data. So then the typical question there is for that to work, you need to really understand the backgrounds, right? To really estimate them very, 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 very well. But I was also wondering if there is an equivalent of the look elsewhere effect, that you're only taking a particular type of data to make this discovery. I don't know if there's an equivalent in.
So yeah, that's a very good point, that we have to be, when we're limiting the amount of data that we store, as we do in scouting, we have to be very careful about making sure that we have enough data and enough information to do a proper background modeling, right? And this is something that is sort of embedded into the design of these kinds of techniques, because it's like, otherwise you can really mess up if you don't account for that, right? In the case of the 4 mu, in the case of the eta to 4 muon, we do all data-driven background modeling, and we can do that by, for example, for the combinatorial background, which is just random muons that happen to be in the mass range of the eta, mass and decay, right? In that case, we can get the same spectrum, because random combinatorial muons, we can invert the same charge, the opposite charge requirement, and derive a spectrum that looks exactly like the combinatorial background. So maybe I can go back, show you like the yeah. So yeah, so here, so here, this, we can look at the side bands and we can study the side bands in data to really understand what's going on, right? And we know that this is mostly the combinatorial background, which comes from just random muons producing this invariant mass that fits there, right? And so, but we do take precautions to make sure that we can estimate those in data. Yeah.
Okay, thank you. Yes.
So I guess Walter has a question. Well, at least he.
Well, I have a very naive question. So for these searches for very light or sub-GeV dark matter with the LHC, how are the prospects or the capabilities compared to the current experiments with the detection of for light dark matter that they rely on the electronic recoil rather than the nuclear recoil, like Sensei and I don't know, some branches of xenon?
Yeah, so that's that's also a good point. The summary plot that I show you doesn't really include a lot of this recent developments in the space of direct detection, which is actually kind of very exciting too. And as you alluded to, you can lower the mass sensitivity of direct detection experiments by focusing on the electronic recoil between the dark matter and the electrons, instead of the nucleus. And because the electrons are much lighter, you can sense much lighter dark matter recoils. So let me put the. Sorry. Yeah, just to have this plot. I think I went too far, no? Yeah, so you can see here that this plot doesn't actually have some of the projected limits from recent experiments, but like recent experiments are starting to probe this region here, going to also sub-GeV dark matter, so around 0.5 and 0.3 GeV in the WIMP mass, with cross sections still not, you still can't get the same sensitivity as you can here, like 10 to the minus 46 at this low mass, but I think they're already targeting 10 to the minus 40, 10 to the minus 42 in the interaction strength between the dark matter and the STEM model. And the searches that I show you, sort of the idea that I show you is slightly different in the sense that we're trying to probe a dark photon, right? And the coupling here is between the kinetic, it's a kinetic mixing between the dark photon and the STEM model, not exactly this dark matter. So the nice thing about the colliders is that independent of what dark matter does or not, if we have this portal, like the dark photon, there are other portals, but like the dark photon, if the dark photon happens to exist, it necessarily must interact with the photon. So we can look for that in this way. So they're very complementary. It depends a lot on the kinds of models that you assume for dark matter, right? But for example, if you have a complex dark matter, complex dark sector here, even this limits on this dark matter could be evaded because you can say, oh, you have a heavier dark matter state that decays to the light one. In different, they have co-annihilation. So it's easy to evade the stringent limits. I hope that so yeah. Does that make sense?
Yeah, thank you.
Mm-hmm.
We have a question from the YouTube people that is following the transmission. Andre Leza is asking, is it possible to use data scouting and still reconstruct the MET, sorry, the missing energy?
Yes, it is. And in fact, yeah, there is so I gave you the example of the muon scouting, but we have another scouting stream that reconstructs jets, for example, only jets, right, instead of muons. There you can have, if you measure all the hadronic activity, you can come up with a very coarse idea of MAT, of missing transverse momentum. But in run 3, which is the latest data taking run of the LHC that started in 2022, we actually have a very nice scouting that's called PF scouting, where we're saving all of the particles in very reduced format because of advances in compression techniques. So we have a better scouting stream that will allow us to actually reconstruct the missing transverse momentum. And this is already being explored, for example, to see if we can reconstruct tau leptons, because tau leptons always decay to a neutrino. So there's always a missing transverse momentum component there. But there's been promising work on that, interesting work on that area. Mm-hmm. Not in this data that I'm talking about, which was collected in run 2, which was 2016 to 2018.
Okay, so okay, maybe Andre want to do a follow-up question, but for the moment, I also have a question. I was wondering regarding to PADME, and also the point that you were explaining us in the beginning about the low PT in LHC is very. I mean, there are it's too much data that cannot be handled by the experiment. So this is a good example of in which the fixed target experiment are more robust, because in that sense you are catching all the, let's say, all the data that is going in the direction of the beam over the target. No, I mean, just
yeah.
Of course, there are different energies and luminosity is completely
exactly yeah.
So
yeah, the order, yeah, they're very different luminosity. So you know, we still have to be careful in just different ways. Like, so that's why we have this hole in the calorimeter. If we didn't have the hole, then we would be swamped by the background also, right? So even here we have to be careful about you know,
the low PT
having too much data, too much stuff. Yeah, in this case it's different. It's a different set of constraints, but yeah, but the fixed target, well, the fixed target is nice in the sense that, you know, it's much easier to build a fixed target experiment than a collider experiment. And yes, it's generally a cleaner signature. The other thing, of course, is that we have a positron beam, not a proton beam, and so there's no hadronic effects there. So this is by definition also much cleaner, you know, world. But you know, if you had a lepton collider, that would also be cleaner compared to the LHC.
Mm-hmm. So yeah, thanks. Andre Lesa, he says, great, thanks. Yeah, but regarding with the question, because my second question was related to is it, because at some moment I lost the connectivity with my internet. Sorry, the PADME is it would be able to scan this region that was some years ago with this Hungarian experiment, the Atomki.
Right. Yeah, that's exactly this. Yeah.
Dark photon scenario, because I guess in that part I lost connections. I couldn't follow this.
Yeah. So right. So this is one projection for what, you know, the PADME could probe. Now there are some existing constraints, but in this green space, this will be a 17 MeV particle, and then in this white space in green, that's where, you know, it will be compatible with what the atomic experiment found. So I should mention, this is one theory projection for. So you can there's this link here you can check, but this is for I want to say for pseudoscalar, but there's another set of projections for vector. And sorry, this is for vector, and there's another projection scale for pseudoscalar X17. And in that case, we wouldn't totally exclude the parameter space available, but it would still constrain quite a bit. So yeah.
Yeah, that's true. Yeah, because it's PADME. I mean, even though you talked about the dark photon scenario, yeah, you could change the mediator to explore other type of models. I mean, like you said, pseudoscalar, scalars, or other type of mediators that are not. I mean, you presented one for dark photon, but could be also explore other scenarios.
Yeah, not all of them, because because now there's 3 results. So the 3 sets of results, actually there's an interesting paper by some folks at UC Irvine, where they sort of map the different experimental results, and like there's only a set of possibilities of the mediator that makes sense for all 3 results, and those are the 2, you know, say pseudoscalar and pseudo vector.
Oh, okay, cool. So, is there any other question for the people?
Maybe I have a quick one, not very scientific related, but thank you, Andre, for this wonderful talk. Even from an astrophysicist, this was very, very, very nice. Is there like a science citizen, I don't know, watch out, like in gravitational wave astronomy, they have web page where people from the public can try to characterize glitches that are also in astronomy, people trying to characterize galaxies. Is there something similar in the particle community physics that you can share with the audience, if it exists, where people can do science and help you with this big data problem?
That's an interesting question. So are you saying, like, you know, that people can access the data and then try to...
Well, yeah, or like an interface where people can just help in some way. Yeah, I don't know, like even mathematicians, they have something where people can use their computers to look for really large prime numbers. So they just install some, it's called Mersenne primes. But yeah, like something like that. Is there something similar that the particle physics community have?
So for example, in collider physics, we have this idea of the open data. So CMS, for example, and I think Atlas also does that, but CMS has been doing that for a while now. We release our data set to the public. And this is called CMS open data. And it's, you know, there's some delay in releasing. We don't release the latest set of data, but we release, you know, a pretty substantial set of it. And you know, we have like instructions for how you can access this and do physics analysis by yourself. It's very, I think it's very, you know, people who made this put a lot of thought and effort into this, so it's very nice. And you can access that, and you can download the data for yourself, and you can look for you know, for peaks like this, you know, like, yeah. So definitely there's stuff like you can do it, yeah, like peaks on like this one. And I would definitely encourage people to play with this. So you can just Google CMS open data, and I think will be easy to find. That's one example of something like that. I don't know if we have a general, you know, website space for people to. That would be cool. That's a good idea.
Thank you.
Yeah.
Okay, I guess for the sake of the time, we are gonna finish the webinar here. So first of all, thank you very much, Andre. It was very, I mean, the webinar it was very nice, and especially for the audience that is not the expert in the topic. The beginning is gonna be very useful, especially for the students that are following the webinar. So thank you, Andre.
Thank you very much for inviting me. This is great. Yeah.
Yeah, and for the people that are following the transmission and all of the audience, we invite you for 2 weeks more in May 22. We are gonna have a Paul Ramon. He's gonna be giving a webinar, so stay tuned for the next webinar in law physics. Thank you very much, and see you.
Thank you, Andre. Bye-bye.
Bye.
Yes. Bye.